What do plants and words have in common? I'll give you a hint. It's on the whiteboard. Both of them have stems. For a plant, the stem is the central part that connects it to the leaves, the flowers, the fruits. And for a word, each of the words have stems too. Today we'll be talking about stemming. Consider the word connect. This is a stem for words like connected, connection, connect, and of course the word connect itself. Reducing each of these different words that I've listed over here to connect is the process of stemming, in which case the connect is the base form of the word. Let's say, for instance, you want to become a millionaire. Honestly, who doesn't? So, what's the first step that you take to know how to be a millionaire? Lot of questions, right? Perhaps you start off with a search query. You pull up your favorite search engine and you type in how to invest so that I can become a millionaire. And what you'll notice is the search results that pop up don't just have the word invest, but also have words related to invest, like invested, invest, investment, and so on. The process that is making all of this happen so that you can receive relevant search results which cover all the different variations and all the different forms of the words, like invest in this case, is stemming. That's what the magic is. So today we'll be saying about stemming, what it entails, how it's used, comparing it with another alternative, seeing an algorithm of stemming, which is called a stemmer, an action, and ending with some caveats. Stemming is a text pre-processing technique that's used in natural language processing. Natural language processing, or NLP, is a sub-branch of artificial intelligence. It's the way our computers, machines can understand how you and I communicate using text or speech. Natural language processing includes different tasks to take all of our documents or all of our data set and break it down into smaller components. Let's say you have a set of documents. You continue breaking it down into smaller components to make it more easily digestible for your machine. So each document can be broken down into paragraphs. Each paragraph can be broken down into sentences. And finally, each sentence can be broken down into different words. And these words over here are what are called as token. And this entire process that we have done of taking the data set from the documents to the paragraph, to the sentences, to the words is called tokenization. Stemming as a technique operates at the level of tokens. And now we'll take a deeper look into how that looks. So you got a glimpse of stemming, but there's also another text pre-processing technique called lemmatization. Let's take a look at the differences between the two. Stemming tries to cut the ends of the word in the hope of getting to its base word or its stem. In this case, happy would cut the Y and make it happy. But in lemmatization, it tries to get to the normalized form of a word, that is, the word form that already exists in the dictionary, in which case, happy would just stay happy. As you can imagine, stemming is more of a heuristic algorithm and is very rules-based. It looks at the ends of the words and tries to guess or tries to estimate what the base word could be. For example, it would look at words ending in ing and remove the ing to get the base form, which in this case works. However, consider the word nothing. It tries to apply the same logic to it, and you end up with not, which is not really correct. Lemmatization, on the other hand, would actually give you nothing. But the caveat here is that it requires more context. It requires information like part of the speech, the context of the word, how it's being used, and it uses all of that with relation to something called as WordNet. WordNet is a huge graph which gives you relationships amongst different words, their synonyms, the type of definitions that they have, so on and so forth. That goes to say that stemming is fairly easy and simple to implement, whereas lemmatization is computationally more expensive, but also more accurate. Think of an example where you have the word better. The stem of it would result in better, which is also incorrect. But lemmatization, powered with that additional context and additional knowledge, would actually be able to tell us that better is a form of good. Choosing one or the other really depends on your use case. If you want high accuracy, but you're okay with compromising on it being computationally expensive, go with lemmatization. If you want something that's simpler and easier to implement, while compromising on accuracy a little bit, go with stemming. Now, let's see what the use cases of stemming are. Why should we use stemming? First one is search engine or information retrieval. Think back to our example of wanting to become a millionaire and putting in a search query of how to invest to become a millionaire. Even though your query has the word invest, the search results and documents that come up has the word investment, or maybe investing, or invests. This is where stemming comes into play. Trying to get all of those different forms, the different morphological variants of that particular word, invest. This in turn gives you more relevant results, thereby increasing the efficiency of the search, while also increasing the accuracy of the results that you get. The next use is dimensionality reduction. All of the different unique words that exist in your documents is what comprises the vocabulary, the entire vocabulary. Let's say, for instance, you have change, changing, and changed in your vocabulary, which are 3 unique words, making your vocabulary size 3. If instead you were to use only the stem for it, which in this case is change, your vocabulary would now reduce to just 1 word. This leads to a reduction in dimensions or the number of features that your machine learning model will now have. It again increases the accuracy as well as the precision. This helps you get better performances with statistical NLP models, especially the ones concerned with word embeddings and topic models. Well, enough talk about all of this. Let's go and see how exactly a stemming algorithm or a stemmer works. So hopefully you're on board with stemming, but now let's see the algorithm in action. A stemmer is what a stemming algorithm is called, and let's see how that works. One of the most widely used stemmers is called the Porter's stemmer. And the way it works is that it looks at each word, it identifies the consonants and vowels present in there, and then it does a bunch of substitutions, eliminations, based on the number of consonants and vowel pairs present in there. Let's say, for example, we have the word caresses. And these are the 3 rules that might apply to caresses. You look at SSES present and replace it with SS, or you look at SS present and keep it the same, don't replace it, or you look at S and just eliminate it, that is, replace it with nothing. As you can see, for the word caresses, more than one of these rules would apply. But the trick over here is to look at the longest matching substring, which in our case is SSES, and apply the first rule over here. So this will then become caress, which is correct. Let's say instead the word was caress. In that case, SS would stay the same, which is again caress, which is also correct. However, nothing in life is perfect, and the same goes for the Potter stemmer. Let's look at one example which showcases the limitation that the stemmer has. Consider the word therefore. I've identified each of the consonants and vowels present in this particular word. Let's look at these. So, two consonants coming together, we can collapse them and make them one. So that's C. Let's also look at the pairs of VCs, that is a vowel and a consonant coming together. As you can see, there are three of those occurrences, 1, 2, and 3. In which case, we would denote it as VC raised to the power the number of times it appears. In this case, 3. And finally, ending with the V over here. This particular exponent, 3 over here, is called as measurement. And based on the algorithm, there are certain rules that apply to the exponent. One of such rules, like the ones that we saw over here, says that if the exponent is non-zero, which means it is greater than 0, which it is for our case, and if the word in consideration ends with an E, you must eliminate E, which then gives us this as our stem. Therefore, minus the E, which is incorrect. Even though this is a limitation of the Potter stemming algorithm, Potter stemmer still remains one of the most widely used because of the amount of rules that it has and the amount of correct results it does give, even if stemming as a whole is heuristic and simplistic in nature. Another stemmer that you might have heard of is called the Snowball stemmer. It's a modification of the Potter stemmer. The Potter stemmer was created only to be used with English words. However, the Snowball stemmer is multilinguistic, which means it does work on languages other than English. The Pythonic implementation of Snowball stemmer, which you can use using NLTK, which stands for Natural Language Toolkit, which is an NLP package available, has Snowball stemmer in the event where you can use it to remove stop words. So stop words would then be eliminated from the process of stemming. So those are two ways that the Snowball stemmer is different from Potter stemmer. Let's continue looking at some more issues and limitations that exist with stemming. Two of the most common issues that arise with stemming are overstemming and understemming. Let's take a look at some examples. Consider universal, universe, and university. Overstemming, as it sounds, overdoes the stemming part or removes too much more than necessary to the point where the words can lose meaning themselves. The stem for each of those would be universe without the E. And based on our knowledge of the English language, we know that this is incorrect because universal, universe, and university are three words that mean totally different things. The opposite end of this is understemming, where not enough removal has happened. Consider the example of alumnus, alumna, and alumni. Alumna and alumni would remain the same, whereas alumnus would become alumna, giving us three different stems or three different base words, which in this case is also incorrect because each of these three words mean the same thing and so should have the same stem. Some of the other challenges that exist with stemming are it fares badly with named entity recognition. For example, you might have some proper nouns. Consider Boeing. Based on the examples that we've seen previously, stemming would reduce the ing from it, giving you the stem of bow, which we know is incorrect because it's a proper noun. Another example might be that of homonyms. Consider rose, the flower, and rose, sun rising, past tense of rise. In this case too, the stemming algorithm would inaccurately get the stem for each of those as rise. which does make sense for the sun rose, but does not make sense for the flower rose. You might also run into issues trying to attempt stemming on languages like Arabic, which have complex forms present, as it can be difficult to understand what suffixes and what prefixes are present. Stemming is a simple yet powerful technique when used in the right way. Hopefully, you learned something useful along this way when we talked about stemming, and this has continued to grow strong roots as you go on in your journey of artificial intelligence. If you like this video and want to see more like it, please like and subscribe. If you have any questions or want to share your thoughts about this topic, please leave a comment below.